For today's lesson, we are going to look at linear programming, and our two objectives for today is that we are going to be able to find the maximum and minimum values, and also that we're going to be able to solve problems using linear programming. So let's look at how to find the maximum and minimum values. So linear programming is a technique that identifies the maximum or minimum value of some quantity. This quantity is modeled with an objective function, or sometimes it can be called the maximizing and minimizing equation. Okay, we're going to call it today the objective function. Limits on the variables in this objective function are constraints, which we write them as linear inequalities. Okay, the last lesson, 3.3, we looked at graphing systems of linear inequalities, and that is what we are going to continue to do today. Is we're going to figure out what our constraints are. They're going to be modeled as linear inequalities, and we're going to be graphing multiple inequalities and finding that region that we talked about was our solution. So the constraints form a system of inequalities. The region that solves the system of inequalities called the feasible region. It contains all the points that satisfy all of the constraints. So just like we looked in the last lesson, how that region, if we checked a point in that region and plugged it into our inequalities, we found that it worked out. Same thing happens here. If we pick a point within our feasible region, it's going to satisfy our constraints or our linear inequalities. So the minimum or maximum value of the objective function will always occur at a vertex of the feasible region. And a vertex is the corner of the region where two of the constraint lines intersect. Very similar to what we've done earlier, where we looked at the points of intersection for both equations and inequalities. So that point now we're going to call is our vertex, and it's going to be at the corner of our feasible region, and we're going to find that always our minimum and maximum value is going to fall at a vertex of our feasible region. So that's our property for today. If there is a maximum or minimum value of the linear objective function, it occurs at one or more vertices of the feasible region. And we'll find how this is true in a few moments. So let's jump into the first example. We here want to find the values of x and y that maximize and minimize p if p is equal to negative 5x plus 4y. And these over here are our constraints. So our first step is that we want to graph our constraints. So on our coordinate plane, we're going to graph each of these inequalities, which we know to graph them, we just consider them to be an equality. So think of this as an equal sign, graph that line, and then make sure you shade in the right area. Okay, so for this first one, we'd be shading above the line and below the line, and for this third one, above the line. You're going to find, once you graph these lines and shade in the right region, that this area here in red is our feasible region. Okay, so if we picked any point in this feasible region then and plugged it in for our inequalities, we would find that it would check and it would work. So jumping to step 2, we want to find the coordinates for each of our vertex. Okay, and we said in our last slide that our vertex is at a corner of our feasible region. So we see that if you were to find find point A here, our vertex, you would want to solve the system of equalities here. So we have our two equations. If you solved using substitution or elimination, you're going to find that the solution is 1, 3. Okay, or you can just look at the graph, which is what we're going to be doing in this lesson, and just figuring out where that point is. So we see that the solution is at 1, 3. Same thing for point B and C. We find that our second vertex here is at B, which is 5, 4, and the third vertex is at point C, which is 4, 1. And each of these is a solution to the two equations given. So now that we have our three vertex, our vertices, we want to plug them in to our given equation. We were told that P is equal to negative 5x plus 4y. So here we listed each of our vertices, and we are going to plug them in for x and y. So our first one here is P is equal to negative 5x, and we plug in a 1 there for x, so negative 5 times 1 plus 4 times y, which is our 3. So we have negative 5 plus 12 is going to give us a positive 7. Then for vertex B, we want to plug in 5 and 4, so that gives us a negative 25 plus a positive 16, which results in a negative 9. And then point C, 4, 1, we plug in also negative 20 plus a positive 4 gives us a negative 16. So just to review our steps here, we first graphed our constraints, then we found our different vertices, each vertex we found. In this case there was 3, sometimes there'll be more, and then we plugged in those points. Now we were told in our last slide that according to this property, if there's going to be a maximum or minimum value of a linear objective function, it's going to occur at one or more of the vertices in the feasible region. So in order to find our maximum and minimum for our equation given, we want to look and see which values are the highest and lowest. And we see that 7 is greater than negative 9 and negative 16. So when x is 1 and y is 3, which was our vertex here, then P has a maximum value of 7. And when x is 4 and y is 1, P has its minimum value of negative 16, which we see here. So once you plug in these points into our equation, you want to figure out which one has the largest and smallest value, and that will automatically be your maximum and minimum because those points are at our vertices. Jumping into another example, we want to look at how to solve problems using this linear programming. So same ideas as we did in example 1. Now we're just going to use them in an applied problem here in example 2. So reading the problem, we have a furniture manufacturer who can make 30 to 60 tables a day and from 40 to 100 chairs a day. It can make at most 120 units in one day. So at most, this manufacturer can make 120 tables or chairs or a combination of both in one day. The profit of a table is $150 and the profit on a chair is $65. How many tables and chairs would they make per day to maximize profit? Obviously a manufacturer is looking to make the most money in a day, and so they want to figure out, okay, what combination of table and chairs, how many should I make of each in order to get the most money out in a day? And we also want to figure out how much is the maximum profit. So as always, we want to define our variables, and in this case we're going to let our x be the number of tables in a day and y be the number of chairs made in a day, and then we're going to let p be our total profit. So then we're going to relate using a table in order to organize our information. So we have our columns, which are our tables, our chairs, and our total, and then our first row here we look at the number of products. Well, we don't know how many products we're going to make in tables and chairs, so we're going to just use our variable. So number of products for tables is x, number of products for chairs is y, and the total is a combination of the both, so x plus y. Then we're going to look at the number of units. And this is where we go back to what I underlined here in purple. So the manufacturer can make 30 to 60 tables in a day. So we write that as an inequality. 30 is less than or equal to x, which represents our number of tables, which is less than or equal to 60. Same thing here for chairs. We know we can make 40 to 100 chairs a day. So 40 is less than or equal to y, which we said represented our total number of chairs, and that is less than or equal to 100. And then our total we're given also in the problem, the manufacturer can make at most 120 units in one day. So that's our total here. And then we want to also look at our profit, because that's the goal here is to figure out our maximum profit. So we know that the profit from tables is going to be $150 per table. So we write that as 150x. And then for our chairs, it says a profit on a chair is $65. So we want to write that as 65y. And then our total, once again, is x plus y. So 150x plus 65y. Now we want to write our constraints. So we do that by looking at the information given in the table. And we know that our constraints are inequalities. So we have these first two, which relate to the tables that we have. X is greater than or equal to 30, and x is less than or equal to 60, which we got right here from this part in the table. Then we also know that with our chairs, we can make at least 40, so our y is greater than or equal to 40, and y is less than or equal to 100, because at most we'd make 100, which we got all from right here. We just broke it up into two inequalities. And then we also have our total, where x plus y, our number of tables, plus our number of chairs, will be at less than or equal to 120. So now that we have figured out those constraints and we have our objective function here, which is our profit is equal to 150x plus 65y, we want to follow the same steps as we did in example 1. We want to graph these constraints. So you can see we matched up the colors here to the lines here, and we have 5 different inequalities, and they make this red feasible region. Step 2, you want to find the coordinates for each vertex. And in this situation, we have 4 different vertices. And we see that they're at 30, 90, 60, 60, 60, 40, and 30, 40. Which you can see if you look at the correct scale of our graph, that those are our different vertices. Then step 3, same as before in example 1, we want to evaluate P, which is our profit. Okay, we want to figure out what our maximum profit will be. And in order to do that, we need to evaluate at each vertex. So we wrote down our original equation again, 150x plus 65y, and we're going to plug in each value for x and y for each vertex and figure out which value they give us. And then we want to look for our maximum and our minimum. So we plug in 3090, we get 10,350. When we plug in the point 6060, we get 12,900. When we plug in the point 6040, we get 11,600. And when we plug in the point 3040, we get 7,100. So we can see here in the red that our largest amount was 12,900. And that's going to be our largest or maximum profit that we can get. So we wrap it up here in a sentence. The furniture manufacturer can maximize their profit by making 60 tables and 60 chairs. And we know this amount from our vertex. Okay, our x represented our tables and our y represented our chairs. And we found that we can make the most profit here, this 12,000, if we have 60 of each. And then we also wrote the maximum profit is $12,900. Okay, now it's time to complete the problems that you have at the back of your notes packet and answer the questions that are given. There will be a quiz at the beginning of class, so make sure you have filled in all the blanks. And if you have any questions about how to solve the 2 problems given, feel free to go back and watch the video again. Good luck!